The addition reaction, it gives us dihalogenated alkane. Okay, it gives us this is the main first product. Okay, the product is a CO2 with the two halogens. Each halogen add on the one of the sp2 carbon. So those carbon we add with chlorine, with halogen. And so this is the main first product. This product goes through elimination, give you the what we call a vinyl chloride. It is the material to make the PVC pipe, which is most gardening hose, it is using the PVC plastics. The PVC plastics is a little more toxic, so it's not suitable for food grade. Plastics, there are many others that are more suitable for food grade. PVC is more for just irrigation, deal with a more durable and more workable, so easy to deal with. The halogenation reactions, what do we find out? The halogenation adding halogens, the two halogen atom is added on the opposite side of the double bond. So use the cyclopentane, simple pentene as example. We add two halogens, two bromine, one bromine on one side of the plane, and the other halogen is on the opposite side. So this is what we call anti-addition, because the stereochemistry, the stereoisomer for this dibromocyclopentane, it is an anti-isomer. You can be either this way or this way. These two are the mirror image of each other. So it's a pair of enantiomers. And so we have the anti-addition. The anti-addition reaction mechanism, we start from the understand why this kind of halogen can be reacted. The halogen is highly electronegative. So when the two halogen atom together, and if one halogen pulls the electron slightly harder, just because the can what do you call it? Very brief moment being polarized, then one of the halogen will be slightly positive, the other negative, and the positive end, it is the electrophile. Okay, this be the attracting electrons, and nucleophile can attack the electrophile. And here the alkene being the with the high energy pi electron, it acts like a nucleophile. The high energy pi electrons, which is almost like a lone pair electrons. So that can form bond with momentarily positive charge bromine. This bromine molecule is basically polarized because the dispersion force, just like dispersion force. A non-polar molecule, because the electrons move not quite equally, distribute not quite equally. One part more positive than the others. And so the alkene, the pi electrons, act like a nucleophile to attack. Okay, so to attack, supposedly if they combine the bromine with the bromine, we might have a positive charge ion. And well, this is what I think when the alkene is attacking the protonation, you would have a carbocation. But with the bromine, it's a different story. And this is just supposedly attacking a positive charge. You should get a carbocation. And the carbocation, then you have a reaction. Problem with the carbocations, the carbocation intermediate cannot explain the anti-product. If the reaction intermediate is carbocation, then the bromide, the nucleophile, should attack from both sides, and you will get both the syn and anti-product. But the reality is we only see the anti. So what we really find out is this mechanism we need to know. It is this reaction, it goes through form a cation intermediate, but the cation is not a carbocation. It is actually the bromine form a ring with 2 carbons in the alkene. And this ring, it is three atoms in the ring. It's very stressful because the angle is only 60 degrees, but it can be fairly stable. We call it bromine ion. This name bromine, if you notice in the periodic table, almost all the metals named after end with NiUm. So this is basically shows it's a bromine. It's a bromine cation. Say bromonium ion. It is basically a bromine cation. It forms this product. So the arrow is kind of strange. When you do the homework, you might have to pay attention how to draw the arrow. This arrow is the pi electrons form bond with bromine, and this same bromine atom with a lone pair form bond with this carbon. And at the same time, the bromine bond break. So these are 3 arrows altogether. Okay. This arrow, it is to break the bromine bond to form a bromide. Okay. And the bonding start from this arrow, by the way, start from pi electrons. It's all initiated by the pi electron. Pi electron form bond with the bromine, and then you have the single bond forms. And to form a ring, this bromine will have to give away the lone pair to form bond, so they can form the second bond in the ring. And this bond leaves. So that's, you got 3 arrows all work together. You get a bromonium ion, which is like this. The bromonium ion has been proven. The chemists detect this, the NMR spectrum. Even though it's very unstable, we cannot isolate the compound and determine structure. We actually use a spectrum. From the spectrum, the feature of the spectrum, we analyze and we realize there's a bromine as a cation. So this is bromonium cation is the key reaction intermediate. By the way, the reaction can also happen on the other side. So the reaction actually gives us a pair of enantiomers. This is a pair of enantiomer. And bromine has a positive charge, have 2 lone pairs. Let me see. Have 2 lone pairs. So the reaction actually have a pair of enantiomers as a reaction intermediate. And then the next step, the final step, the bromide attack. This is a simple step. Bromide attack either here or here. And with the enantiomers do the same, can attack here and here. So either way, when the attack happens, this is similar to the substitution, by the way. The last step, it looks like addition step, but the arrow looks like a substitution. Substitution means you form a bond, the arrow comes in form a bond, and at the same time, for the carbon to maintain the octet, need to break this bond. So form bond and break the bond happen at the same time. And so the bromine attack on the bromonium ion can have 2 products. With this one, can have 2 products. With the enantiomers, you got another 2 products. But very easy, we can easily realize eventually there's only 2 products, because with the 4 possible products, 2 by 2, 2 of them are the same, and the other 2 of them are the enantiomers. So that's how the bromonium ion attack give you the anti-product. Okay, this explained why this reaction gives us an anti-product. Okay, like this one said, is very kind of similar to the SN2 process. You form bond, and then another bond breaks. So that's the bromonium ion intermediate, give you anti-product. So the anti-product, we get this. To predict the product, this is the, you basically write down the reaction intermediate. You get either bromines, both are wedge. And with bromine both on the wedge, the bromine will attack from the backside, or with dash. Yeah, so you get these two products. Okay, so this is the reaction. By the way, these two molecules, if we decide RS, these two are the enantiomers. Let's do a quick practice on what is RS for. There are two chiral centers on the carbon. So this is the, if this is number 1, this is number 2, 3, and 4. 1, 2, 3, 4. So the naming for this chiral center, and there's a hydrogen as the dash, which is perfect. And start from bromine is number 1, the top priority. And this carbon will be number 2, second priority. And this is number 3. So this will be the R. This carbon will be R configuration. And with this atom, the number 3 carbon, and the hydrogen is on the wedge, by the hydrogen on the wedge, close to me. So that means I decide the priority to clockwise, counterclockwise, and then I need a flip. This is number 1 ranking, number 2 ranking, number 3 ranking. So we got a counterclockwise, but that's is with the hydrogen on the wedge. In reality, the bromine, this is the ethyl with methyl, it should be clockwise. So this will be the R. Both carbons are configuration. Okay, so with this molecule, I realized the compare with my first molecule that I discussed. This is the just opposite to the number 2 carbon in my first molecule. So without even trying, since I decided the first one's R and R, this must be S and S. So you have time, you go home, watch this video. You can do the RS configuration. You notice this is the RS and S molecules. The both chiral center SS. So we'll get a one pair of compounds is RR and SS. We do not have the RS compounds. There's no RS compound. Start from the cis-2-butene with the addition with bromine. We have only the RRs and SS, a pair of enantiomers. And so this practice is just kind of a little extra practice, right? A staggered Newman projection along Cs 2 and 3. So this basically show the, we start from the Newman projection. This Newman projection on the 2 and 3 carbon. And with 2 and 3, I put a methyl group here and the hydrogen being here. This is cis, so methyl group is on the eclipse position. All right, so that's basically we start from, this is the reactant looks like. Now we add a bromine. Add a bromine will be one bromine add to here. Since it's the anti, the bromine add to the other bromine on the down position, because this reaction is the anti-addition. Remember, it's the anti-addition. So once getting here, I can just transit, make all the bond 120 degrees, all the bond angle 120 degrees on this projection. So this structure relax becomes this product. And so the anti-addition reaction, if you start from Newman projection, we'll deal with the just normal cis and trans, no rings. It's easier with Newman projection. Start from Newman projection and add the bromine on the opposite side and give us a final product. So this, it will be our first molecule. It's our first molecule. Okay, so the little extra practice explain how does the halogen been added and what is the stereoisomers we get. Is we get the we get the RR and the SS. Okay, what about this is a little extra practice? If the bromination from trans to butene, we can write down the trans butene structure first. And then we add a bromine. Bromination means adding the Br2. This reaction, since anti, and we need to do the slow. Okay. With this molecule, the first one, I would add the bromine on the wedge, and the other bromine is on the dash. And then the we need to keep track on the other methyl and hydrogen. So here hydrogen, CH2. CH2 I used to just write down Me, methyl. Anyway, so that's a real full molecule structure. How this addition happens is we add the one bromine here. It's basically add the bromine on my side. Okay, this is the bromine on my side. And the other bromine add on here is from the other side with the dash. Okay, so this bromine I add from my side will make the wedge. So that means the methyl group being pushed away, hydrogen being pushed away. So we have methyl group and a hydrogen, both being pushed away. Make sense? We add a bromine atom from my side.
No.
My side.
Well, okay. How do you know which side is your side? I'm confused.
I just randomly, arbitrarily defined.
Okay, okay. I think I see where you're coming from.
Yeah. The other way to add in this one, you make the molecule rotate, it might be even harder. Okay. Yeah, I'm not sure this is easier. This is the other way. There's a lot of stereochemistry around in this reaction. You know, with the rings, it's much easier to decide to write the anti-product. But with the open chain, with the cis and trans, be able to, so this is the molecule from this trans, the anti, what do you call it, trans molecule, trans isomers. I rotate it, becomes this. Can you guys see that? I want to make sure you guys see that. The alkene, I put it both close to me and give me that. And then the one bromine add on top, the other bromine add from the bottom, give me the product. So I think this way might be a better way to draw the structure. Let me finish whatever I just started. And so I add the bromine from my side. Okay, this is a big wedge from my side. Methyl group being pushed away. Hydrogen keep the same. Basically, I push methyl group away from the middle. And with bromine add on the backside of the methyl group. So that means, okay, watch this. This methyl group being pushed out, becomes wedge. And the other hydrogen stay. there is a changing in the configuration. It is basically from trigonoplanar becomes tetrahedral. Both become tetrahedral. So I think the it's kind of hard to imagine like this. So let me try the other way. The other way is I rotate this molecule just like here. Okay, I'm going to erase whatever here. I'm going to use this molecule. Rotate the entire molecule. Becomes the 2D molecule. Because it's trigonoplanar for both carbons. I use a 3D to represent, draw the wedge and dash. Can you guys see how from this molecule becomes this? Can you guys see that?
Not really.
It is same molecule. It is same molecule and the bonding is still the same.
But how did you decide what was going to be away from you and what was going to be towards you? Like, well, why isn't it the CH3 and the H towards you on the left side?
I just picked them. I just pick it. Doesn't matter. It does not matter. Remember, it does not. You're supposed to predict all product. So you have to basically just pick any. Basically, on the same side of double bond, I make them both wedge. Make sense? They're on the same side of double bond. So they have to be both wedge. And the other away from me, both will be the dash. Make sense? Start from drawing this structure. And then from here, I think it's easier to add a bromine and give you the final product. So let me redraw this. Methyl group, just use ME, just too much work. I hate using CH3. The same molecule, now I draw like this. All right. So now I need to add the bromine. The bromine, now I add it on the vertically. Okay, add one bromine, add on here. And now there's no more double bond. This is a single bond. And the other bromine is anti-position, add here. There's anti-addition. Good? All right. Well, this is not the real normal bond line structure. Normal bond line structure, we should be able to see the tetrahedral. So how to make a tetrahedral? Now I keep these bromine. They are on the paper, all right? Keep the bromine on the paper. And then draw the normal bond line structure. This is mind-boggling, okay? Mind-blowing. Learning organic chemistry, you gotta be able to rotate the molecules. Can you guys see that? I rotate about 60 degrees, kind of, because I try to make it a normal bond line structure. And what happened to the other group? All right, so this methyl group, it's a circle. Stay away from me. And the hydrogen, notice, is a wedge. So that stays wedge. Do not change. Got it? I just rotate the angle a little bit. Try to make it just like the normal way, normal view. Because what I just added bromine, the shape is not quite a tetrahedral. It's not what we used to see for the alkane. I just try to make it looks like a normal alkane. Got it? Can you guys see that?
Yeah, so essentially you're just moving it like to make it look like what we usually see.
Yeah, we used to see. We're that when we feel comfortable seeing that.
Yeah.
Just adding the bromine is a weird shape. It is kind of in between trigonoplanar and the tetrahedral. But now we make it relax. It's like whole molecule needs to relax to achieve the 109.5 degree angle, more relaxed. All right, so what about this bromine? Same thing happened, okay? Whatever circle, stay circle. Whatever wedge, stay wedge. No change. Now we have see hydrogen is still the delta hydrogen. And the methyl group now is a wedge. All right. And the methyl group is in circle. Okay. Are we good? Yeah, this is the addition reaction, the hard part. It's very similar to the last chapter, elimination. When you do the elimination, you remember you have to rotate the bond so that the hydrogen leaving group will line up at 100 degrees anti-position. So this is similar, but this is just opposite. We'll try to make the structure relax. So that's the product. Okay, we have the trans and adding the bromine, we got this is the product. By the way, we should have got two products. I don't have time to do that. We actually end up has these two products adding the two directions. The other product is bromine add to here, and the other bromine add to here. Adding both each ways are end up give you the same product. The reason because the trans-butene, it is symmetrical. It is the what we call the rotational symmetry. So we get the one product. So anyway, let's decide what is RS, because that can easily show us this is the same product or different product. With this carbon, okay, this is the first chiral center. Let's use the color, make it see better. The first chiral center, we got a bromine, you got a methyl group, hydrogen, and this is kind of ethyl group. All right. So bromine is high priority, number one, right, you guys? I'm doing the RS configuration, the bromine number one. Okay, which one number two? Methyl group or this? Which one number two?
Methyl group. Oh wait, the big thing you mentioned.
No, this would be yeah. It's basically a bromine, bromo-ethyl group. Okay, this should be number two. Sorry, it's kind of confusing. And number three is methyl group, right? Hydrogen is the minimum, the lowest priority. So by doing that, we notice this is a clockwise. It should be R, but keep in mind this hydrogen is a wedge. So therefore, actual configuration for this is S. Got it? This carbon is S configuration.
So Professor, if we were naming that, it would be an S. Like if we were naming that whole entire molecule, it would be S.
No, we have another chiral center. You have to do the other one as well. We have to do both. Yeah. So this will be, the naming will be, yeah, we'll get it to name once we find the RS for the other one. This is also chiral center. Okay, I need to erase all the one we have. Okay, because it's getting in the way, it really can be messy. All right, so the RS configuration for this carbon, which is number 3, by the way. If this is number 2 carbon, this is number 3 carbon. So it's number 3 carbon, hydrogen on the wedge, on the dash. Great, that's perfect. So bromine number 1, highest priority. This is number 2, second priority, right, you guys? This is second in priority. This is number 3, methyl group have a CH3, lowest priority. So 1, 2, 3, that's a clockwise with a hydrogen away from me. Perfect, that's R. So this product, it is a R, second, the number 3 carbon is R. We would get another product if we have the bromine attack here and the other bromine attack there. You get just the exactly opposite will be the R and S. But these two compounds are actually the same because the symmetry in the molecule. This naming will be 2S and 3R. And you can check for yourself. It's exactly same as 2R and 3S. The reason because this molecule it's basically symmetrical molecule. And so you get a pair of what do you call it? It's not a racemic. There's a name for that, a meso. We call a meso compound. So you get a symmetry between the two chiral centers. It's a meso compound. You got two chiral centers, but these two chiral centers have opposite effect on the polarized light. Therefore, have no net effect on the polarized light. It will be called meso compound. Anyway, I think we're pretty miserable dealing with meso compound. By look at the stereochemistry, predict the product, you can see there's a lot of work when you do the addition reaction. Okay, it's a lot of work on the addition reaction. Kind of getting that?
Kind
So,
of.
take some practice. This is really how to take some practice. Addition and the alkenes, it is a little more challenging because you have to add in the two atoms from the opposite side, and you get from the trigonoplanar getting back to the tetrahedral. I think the elimination, if you recall the elimination, we turned the tetrahedral molecule, both the tetrahedral carbons, into the trigonoplanar, into alkene. It's a little bit easier than this. This is you adding those back and return back to the three-dimensional. And with all the bond angles being twisting and relaxing, finally get to our final product. So that's the how we add to the double bond. By the way, if the addition happens on the ring, it'll be much, much easier, as you can see. Yeah, we've seen some examples adding the ring. And the ring is very, very easy. You get an anti-product. You don't have such hard work. But when you have the open chain, the middle, the alkene in the middle, then the stereochemistry. What kind of product you get? RS. But this just kind of give you the what it really takes to get to the stereochemistry, the final product. I think in our quiz we don't have much such kind of questions. Hopefully, okay. And so you can see the addition reaction, stereochemistry. It takes some new kind of practice. We're getting to the end of the chapter. There's more addition reactions. Those addition reactions, I will not put too much stress on the final test or quiz. And you can see from the Zeppelin homework, there's not so much on the addition reactions. I'll go to give you a study guide on Zeppelin homework. You can see that. There's more addition reactions will be similar, and even reaction mechanism, it is similar to the Bromonium ion. This kind of reactions is when the not only the halogen as electrophile, but also water as a nucleophile is in getting the reaction. So the difference is first step is very similar as a addition with a halogen from Bromonium ion, but the next step, the nucleophile is water, no longer bromide, because bromide is a lower concentration than water. Water is more abundant in the reaction conditions. So the reaction product is different and is related to the Bromonium ion intermediate. This is what we find from the reaction. With bromine and water, the bromines, one of the bromines are added, but the somehow it becomes an alcohol, it's a halogenated alcohol. And we call it Halohydrin. It's a Halohydrin. This kind of compound we call it Halohydrin. And the reaction is also anti, as you can see from the ring, is much easier to decide. The enantiomers will be just mirror image. You got these two pair product. And we have two product, and we can name them, decide RS, but we can skip that exercise. You can do that later. The reaction mechanism, I just go quick on this. You're not required to really worry too much about this kind of reaction mechanism. The very first step is very similar, is a 3 arrow. Just 3 arrow pushing. Pi bond form with this, and one long pair form bond with this carbon, and this bond breaks, give you bromide as a leaving group, and then you form the bromonium ion, and then the bromonium ion, next step, if you remember from the halide addition, is we add the halide ion. But here, since water as the more abundant nucleophile is more available, instead it will form just like the substitution. Nucleophile attack and break the bond to break the ring being opened. And then you have this open the ring, water as a nucleophile, so you got a protonated alcohol. Finally, you just need to remove the proton by the nucleophile water, give us a final product. So that's the last step reaction. Use arrows. It'll be just like this. Okay, so that'll be the last step. Give you the halohydrin. This kind of reaction we call halohydration. So because you have halogen and adding water, so halohydration is a 3-step mechanism. This reaction is not the emphasis in this chapter, but when you just need to know. The addition happens, waters add to the carbon with more carbons. This is because in this intermediate, the bromine's high electron activity, that will make each carbon slightly positive, but carbocation or something similar to carbocation is better stabilized by the hyperconjugation near those methyl group. So this carbon has slightly more character of a carbocation than this. So that's why this part is similarly more attacked. Is the main attack happens on the nucleophile attack on this carbon, because this carbon has more character of a carbocation. It's better stabilized carbocation, such as this. Yeah, this is similar to the carbocation. If you remember, tertiary carbocation is most stable, and then secondary, and then primary. This carbon being the carbocation, if have the full carbocation, it should be more stable. So it can be explained just by the by this kind of a something related to the stability of a carbocation to form this product. And so even though the even though there's methyl group, it's kind of chunky, it might block the excess of the nucleophile, but because the water molecule is so small, not being affected by the blocking of this methyl group. So neohydrin reduced selectivity, which means where to react. It is OH attached to the carbon with more substituted. We call it Markovnikov, sort of Markovnikov. By the way, this reaction, if you try to make a connection, replace the, let's say we remove this, just replace by proton. We let the reaction happen in the acidic solution. So that way, hydrogen to replace the bromine, replace the first bromine, it will give us Markovnikov alcohol as a main product. Replace the bromine with hydrogen, then the reaction is similar to this. halohydrin addition reactions happens on the OH attached to the carbon that is more substituent. It resembles the carbocation intermediate. And so you can see the second step, the reaction happens in water, halogen with water. You get OH, alcohol as a final product. But if the reaction happens with halogen in ethanol, in the alcohol, if the reaction happens in alcohol, the reaction mechanism very similar. The difference is the last step nucleophile will be the alcohol. Since the alcohol instead of water being the nucleophile, your final product will be an ether. So the reactions, this is kind of very interesting reaction. With the bromine, with the methanol, the reaction, the first, because the reaction mechanism, bromonium ion, and then this is slightly has a more positive charge, is attacked by the nucleophile, which is the alcohol. In the end, the alcohol, methanol, attack on this carbon, and the bromine will be in the anti-position from the methoxy group. This comes from the alcohol. And you get a pair of enantiomers start from the from this achiral alkene with anti-addition. And this reaction mechanism fairly easy to understand. It's you start from the first bromine from the bromonium ion, and then bromonium ion nucleophile will be the alcohol. Alcohol nucleophile. The alcohol nucleophile attack. I draw the bromine as sort of a wedge. Let's make the dash. Okay, make a dash. That with the nucleophile attack from top. From top, and you break this bond. Wait a minute. Okay, sorry. The attack's not happened on this carbon. I was not thinking. There should be Markovnikov. Okay, not attacking here. Not attacking here. This is my mistake. It should attack on the. You have two carbon ions, carbon atoms. This one being carbocation will be more stable. So that's why the attack happens on here. And this bond breaks, kind of very crowded. This bond breaks. And that's how you get this product. Okay. To get enantiomers, we just need the all-wedge bromonium ion. And then attack from the back. From the other side will give me this enantiomer product. So that's the stereochemistry on the addition reaction. The halogen in alcohol as a solvent, where the alcohol as a nucleophile give you halogenated ether as a product. And so, so far we have about 6 or 7 reactions with addition reaction. Each has its own stereochemistry. So this is to take some practice. We're getting good at this. And we have just a few more reactions. We'll be wrapping up this whole chapter, particularly Halohydrin formation. So basically, how the halogen will be added to the alkene. Notice this is a cyclopentene with a chiral center. So this chiral center is not involved in the reaction. It need to maintain the same, unchanged. The reaction should take place on this double bond. And you have a bromine and the solvent or nucleophile as water. Your product should be an alcohol. And the alcohol, OH, should be attached to the carbon that was more substituent. the more substitute carbon, because just kind of try to remember carbocation on here is much more stable. So therefore, nucleophile attack on this is just more possible. So OH attack here, Br will be here, and maintain the N-type position, because this reaction is a ring, cycloalkene ring, adding the ions in the N-type position, or cis is just much more easier with a ring, and then the product will be very easy to decide. This chiral center not been changed, and so this OH will add on this carbon. Okay, now we have a stereochemistry. It's very important. We need to show the stereochemistry. Let's say the OH attached as the wedge, then the hydrogen, which is not visible, it will dash. And this carbon, you have a hydrogen to begin with, and they add one more bromine. The bromine has the N-type position from the OH, and OH is a wedge, so bromine is dash. And the hydrogen is a wedge. So this is one of the products. And keep in mind the attack from, it can be the other way. They attack the other way, you will get the other product. The other product is not the enantiomer of this product. Okay, it's not the enantiomer, because this compound, you have one more chiral center. This has a chiral center. The other product regarding this section should be completely just opposite. Wedge become dash, dash become wedge. So the bromine now is dash, hydrogen being the wedge. And same with the other one, because anti. Oh, wait a minute. No, sorry, I kind of draw the same structure. Yeah, these are, I'm supposed to draw the opposite from the first molecule. I end up drawing the same. We are talking and thinking is not quite come together very well. The bromine now should be wedge, okay? Bromine's wedge. Okay, so the OH will be here. What should, what kind of bond is a wedge or dash for the OH?
Wedge.
Wedge?
I meant dash.
Dash or wedge?
Dash.
It's anti. It's anti. So it's with dash, and the hydrogen being the wedge. So in this reaction center, we got completely the other way around. But are these two enantiomers? Two enantiomers, all the chiral center has to be reversed. And you can see these two is reversed. These two chiral carbons is reversed, but this is not. So therefore, these two compounds, we have to show them separately and show both, because these two compounds not enantiomer. Because this chiral center maintain the same RS configuration, no change happens. So these are the reactions with chiral center. It made it a little more complicated, but it's nothing really different from the other reaction we've seen before. Okay, so we have a, this reaction is about ask what the reactant and what reagent to give me this product. And to figure this out in this chapter, a little bit easier because we just learned about the Halohydrin formation. And then notice this is the ether group to be added. This is the halogen to be added. Double bond must be here. This must be the double bond. It was double bond, okay? Was double bond. So this is basically reverse thinking. And after we learn this chapter, after we learn about alkene reactions, for the next midterm exam, we'll get into more thinking about a synthesis-driven organic chemistry. We're going to use the reaction that we learned to make new compound. Let's say your supervisor in the research group want you make a certain compound. How are you going to make it? You're going to use the reaction that you learned and to design a reactant and design the reaction condition to get a product. So this is halogen. This is the ether group. The reaction, it has to be the chlorine and the ether. What kind of alcohol depends on what kind of alcohol we use. This ether have a methyl group, ethyl group. Ethyl group is oxygen. So the ether, it will be the ethanol. This is completely thinking backward. Okay, this is kind of more advanced, backward. Halogen come from the halogen in the molecule come from the CO2, and the ether group come from the alcohol, and then the remaining, it is actually the alkene. So let me use a different color for that. This, it'll be the alkene that give me this product, and the double bond being here. So there it is. This is the mystery alkene, and this is the mystery reagent. With these two, will give me this product. By the way, Zeppelin homework, you have seen this kind of questions more and more. And start from the substitution and get into the elimination, you will see something like this. And now we're getting back to the addition. Addition, we see the same. We'll give you the product and ask you what condition to make those products. So just take some more thinking on the, take some practice. Anyway, in our test, this midterm, we won't have this kind of questions as much. It's more advanced and it really require you to get to know more reactions to really come up with ideas. You see more or less in the Zeppelin homework have such kind of questions. And so this kind of question, by the way, in our quiz, in our worksheet, I have similar questions. It's about stereochemistry and you get different kind of product. I will not do the this kind of exercise. If I do, I have to do it quick because you have a whole bunch of this is a reaction with the halogens, anti-addition. Make sure show the stereochemistry. You notice this is solvent is not a nucleophile. CCl4 is not nucleophile solvent. It's actually non-polar solvent. So it does not have nucleophile to react. But with water, alcohol, then you have the nucleophile attack reaction. All three reactions go through bromonium ion intermediates. Okay, they all go through bromonium ion intermediates. And so we have a stereochemistry like this. They all give me a pair of enantiomers, by the way. They go enantiomers. This is methyl group here. And the bromine is added on here, and you got a hydrogen. Hydrogen is the other one. All right, so that's the adding OH. And the last one, adding the, with the alcohol as a solvent, you got an ether as a product. It's very similar as you just seen. This is also you get a pair of enantiomers. But these two reactions very similar. The only difference is you replace the OH by the oxygen methyl group, the methoxy group, replaced by the OH by the methoxy group, which gives us the ether. So that's the reaction with these three. You will see the worksheet and quiz have a similar question, just like this. Okay, and there's more reactions, but these reactions we just need to know the reaction stereochemistry, but we will not be using for asking about the mechanism. So I'll go very quick on that. This kind of reactions, anti-dihydroxylation. So basically, we add 2 OH group on each of the unsaturated carbon on the alkene. Add OH on both, and so the reaction happens. We use the peroxy acids. The peroxy acids are the carboxylic acid, but with the instead of OH, you get a per-hydroxy group, because this reaction give you the oxygen on the double bond. This is called epoxide. Epoxide, later chapter, we'll get into that very soon. In the following 2 chapters, I'll get into that epoxide. And so this reaction first give you epoxide. Epoxide attacked by the nucleophile, by water, give you the ring opening, is a water attack on this. Open the ring, give you the alcohol. So basically that's the reaction mechanism. In this chapter, we just need to know what is the kind of product. The reaction give you okay, this is the peroxy acid, give you anti-dihydroxylation reaction. Give you the alcohols on the opposite side of the ring. Okay, so the anti. The reaction mechanism, I won't spend too much about this. There's one common reagent, it is a meta-chlorperbenzoic acid, the MCPBA. MCPBA, you will see this later very often. It is on the, it is very similar to benzoic acid, but you have peroxy group, and the meta group have chlorine. This is MCPBA. Is the agent to give you from the epoxide and then from diol. And basically a 2-hydroxy group, a diol as a product. And so that's the reaction. Oh, I have a structure. Oh, goodness. Activation attack of the epoxide. This is how the reaction takes place. And the reaction mechanism is just nucleophilic. But again, to make a better leaving group, by the way, the oxygen without protonation is not a good leaving group. So to make it better, break the bond as a leaving group, protonate first, and then you have a nucleophilic attack to open the ring. And open the ring can happen on both carbons, and then each one get a different product. If coming from this direction, you break this bond. So they get a 2 kind of product. Anyway, this chapter we just need to know the anti stereochemistry of the diol. And this kind of shows you similarity among the intermediate that we've seen in this chapter. We actually first seen the mercuration, using mercury to help us form Markovnikov alcohol. And that gives the mercury in the ring, 3-atom ring. And then we see the bromonium ring. And finally, this is one we just mentioned, the peroxide ring. There can be Syn-dihydroxylation. This reaction is using very special reagents. It is osmonium tetroxide. It's basically a compound that is a very high oxidation state osmonium compound. And this gives us a syn alcohol. We don't use this kind of reactions much. So just when you see this kind of reaction, know that reagent gives you the product. Just memorize. We won't be asking that much. They give us, you can see the OH group on the same side of the ring. That's a syn addition on the OH. And permanganate can be also, the permanganate is hard to control. Permanganate also give us, it's very messy if you use permanganate, because it can give you the open the ring and give you the carboxylic acid as a final product. But anyway, we don't use that, and just kind of shows you what the reaction. You don't need to really use that for synthesis or predict the reaction product, not so much. And this is the last part, is the alkene. It can be broken down by the ozone. Is what we call oxidative cleavage. It's basically breaking down the double bond by the ozone. This reaction we just need to know the condition, and that's about it. So what happened is it's very easy to predict the product. Double bond breaks, and each carbon bond with oxygen. That's actually what happened. It's pretty simple. So in this reaction, because this carbon has one hydrogen on it, so in the end, this gives us an aldehyde, and the other product ketone. It's very simple. And so that's the reaction mechanism. We're not interested. We're not going to get into the reaction mechanism. The condition is we first use the ozone is to form bond. It's forming the addition reaction. And the next step is zinc is break up the bond to give you the ketone. So this is your first ozone form a ring. It's very stable. And then you have the reducing agent help it break down this molecule, give us so basically the carbon-carbon double bond becomes 2 carbon-oxygen double bond. That's what happened.